Hello, everyone, and welcome back to HDL for Digital System Design. I'm Dr. Mike Brofchek. Great to see you back here. So we're going to continue on topic 3, procedural combinational logic, the latch problem. So we've already talked about how to wrap things in an always block uh, with a hopefully wildcard sensitivity list. We've talked about using if-else and case statements. Now we're going to actually dive into something that I've alluded to a handful of times, which is the latch problem. So let's dive right in. So one of the things that you'll hear about often in our industry in the creation of hardware, whether that is FPGA based or um, ASIC designs, is something called zero inferred latches. So that's actually something that is on pretty much every checklist that you'd ever receive in terms of like delivering high quality hardware, is that you want to guarantee that there aren't these latches that have been produced that you didn't expect or that you didn't mean to have happen. So tools like Synopsys Design Compiler, Xilinx Vivado, Intel Quartus, a lot of these, even Icarus Verilog, iVerilog that we're using, in some way let you know about latch warnings when they exist. And I will say that many engineers that practice, and senior engineers among them, will treat latch warnings as errors, in the sense that it is not something that you are expecting to have happen. And we'll see why that actually occurs. So in this course, pretty much anytime after this topic, you should be checking for latch warnings. The easiest way in our make files, doing a make stat, which behind the scenes is looking at some statistics from the Yosys toolchain. So Yosys stat is behind the scenes the command that's being run. These reports are going to let you know if there is a latch that was inferred. And so just know that we don't want to see those. And in general, you don't want to see those. So this video is going to give you some tools, some techniques, 3 ways to prevent that from happening, and give you some techniques also to search to see if you have an inferred latch. So uh, there you go. So the first thing to really consider is you might be thinking to yourself, well, I don't have a clocked element in my design. And so far we've said that most latches or latches that we design are clocked elements. So when a clock edge goes high, we want to store something depending on the style of the latch. But the idea is that um, in general, when we mean to have a latch, we usually mean to have them on a clocked interface. Store this value every clock cycle, or store the value of something every clock cycle, because I want to use it. Um, so if you don't have that, right, if you don't have positive clock edge anywhere, or if you don't have a clocked behavior, you might say, well, there's no way that I can have a latch. I have this always block, and I made sure that my sensitivity list, as I was talking about in the first few videos, made sure that that was a wildcard. So why would there be a latch? Well, so it's a little bit more complicated than that, but just consider that if you drive a signal to some value in some condition, so you don't always drive it, you drive it sometimes. If you drive it to some signal and then you don't drive it in other cases, behind the scenes, that's going to be inferred as you want to keep that value even if the value changes. So you drive it in some condition but not others. The question is what happens in those other conditions? The inference is that you want to keep the value you stored. And so that's exactly what's happening. Um, Essentially, if you don't assign the output on some path, there's some set of paths that are possible, you assign it on some and not on others, the synthesizer behind the scenes will infer a level sensitive hatch. Basically, that latch is going to be um, storing the value that you have assigned to hold as long as it needs to. Doesn't require a clock, and basically, what will happen is that latch is observing your conditional signal. So let's take a look in some more detail. But just know that what is happening here is the latches will work in simulation. You'll probably pass many test benches, but behind the scenes, you're creating some unclocked storage. All right, and so that is super dangerous. And actually, in most cases, you won't even find this until tape out, until your design is either on, well, basically in hardware, the FPGA case, or it is in silicon. So super dangerous. So um, here's the big takeaway for an inferred latch, how it can happen. So we've got our always block with begin and end, which is great. We have a wildcard sensitivity list, also great. And then we have an if. If select is true, right, or high, y will equal a. All right, that's actually great. But the question you should ask yourself is, well, if select can be 0 or 1, right, which appears this is the case, right, true or false, well, if we have a branch that says what happens when it's true, what is the behavior when it's 0? Well, so what actually gets inferred here is, well, you don't tell me, but I'm guessing that it should remain at the value that you had held, right? So you didn't tell me what was supposed to happen at 0, so I'm going to hold my previous value. Well, if I have to hold a value in hardware, I need a latch to do so. So that's where basically that latch comes from. Here's another one. We have, again, great always block, begin and end, good. Wildcard sensitivity list, great. And we're going to use a case statement, as we talked about in a previous video. It looks like we're doing a case that is sensitive to the opcode. So opcode here appears to be 2 digits, 2 binary bits. And it looks like when it's 0, 0, y will be A. When it's 0, 1, y will be B. That in itself isn't a problem. But since our opcode can take, it looks like, 4 possible values, what happens when B, well, basically when your opcode is 1, 0 or 1, 1? Well, what happens is behind the scenes, there's no branch here, so I infer that you want to keep whatever value Y last held. And to do that, I need the latch. And so that is exactly what your synthesis engine will do. It'll create a latch there. So here's the rule. If there exists any combination of inputs where your output is not assigned, the synthesizer must infer storage. There's no choice. Doesn't matter what you intend. The tool cannot read your mind, right? It builds what it sees, and if it doesn't see pathways from inputs to outputs, it will infer that you wanted to keep the other values you already set, and it will put in a latch. Okay, so how do I prevent latches? 3 different ways. Default at the top of your block. Always begin, wildcard sensitivity list. The first thing you can put in there is what is the default value? What do you want this to be, assuming nothing else happens? So you set a default first, and then an if, and you aren't going to get a latch because guess what? Every possible pathway is handled. You have a value for y, and then you're changing it if some condition exists. So no other states possible there. All right, 2, if you have an if, put an else, right? So same general idea here. Again, always with a wildcard sensitivity list. If select is true, y equals a. Else, notice there's no if on this. It is a global else, right? It is going to catch any other condition, right? Again, because we're talking about here a very specific binary condition. It's pretty easy, but else y will be 0. So there are no other possibilities there. Select is either true or false. So that if else block will work. All right, looking at the case statement option. So uh, always, again, a wildcard sensitivity list, begin and end. Great. We have our case statement here. And what do? Well, we actually add in a default. So we add in this default that actually does a handful of things for us. One, it will handle our other 2 cases. What happens when our opcode is 1, 0 or 1, 1. It'll take care of that. The default, right? If it's not listed in the cases above, it will default to y equals 0. The other thing this does for us also is there are times when things can get into unknown states or z states, potentially x states. So either unknown or high impedance states for whatever reason, and the default will catch those. So even if you have a fully specified set of branches within your case statement, it is still good practice to put in a default, just in case. All right, so my personal preference in general between 1 and 2 is I'm going to go with the 1 option almost every time. Putting that default up first is a pretty defensive way to do this. It covers both our cases, whether you use an if, um, basically if or without else, and also if you have a missing case, it could actually solve that as well. So in theory, you could throw in that default first right before a case statement. So in general, try to put it at the top of every single always app block that I write. Okay, so your turn. Let's try to do a latch hunt. So question is, which of these blocks will infer a latch? Is it the first one that has an if else there? Is it the second one B where we have a case statement looking at 0, 0, and 1, 1? Or is it the last one where we have that y equals 0 and then an enable y equals a? Which of those do you think will cause a latch? I'll give you a moment. And all right, hopefully what you see here is that no latch on A because we have a complete if else. There will be a latch on B, right? We don't have cases 0, 1 or 1, 0 covered, so Y is going to hold on to that value. And the only way to do that is with an inferred latch. And then C, there's no latch. We have a default on top, so no problem there. All right, your turn. Can you try to predict what you're going to get if you run and synthesize this code block here? You've got an always at block with a wildcard sensitivity list, begin and end, have a case statement, takes in an opcode to get 0, 0, 0, 1 are your 2 cases. What kind of warning do you think you're going to get from Yosys? Any ideas? All right, so what we expect is likely either explicitly saying a warning or some words like latch inferred for some signal. And in this case, the signal where there's going to be an inferred latch is around the result signal. So result is the thing that would have to be latched if we don't have all these paths covered, right? Result is the thing I would have to store while the opcode is changing to things that I haven't seen before. So um, we might see, depending on the complexity of the synthesis engine, a list of conditions for where the opcode is not assigned, where this could be an issue. Again, don't expect this on every synthesizer. The other thing is some synthesizers might also report the estimated latch gate count, and we'll see what that looks like for us as well. So, useful habit to get into if you're a Linux user, grepping your synthesis logs for latch or inferred on every run. I'll tell you that in our sample demos, trying to grep for latch probably isn't great because that's the name of our um, module, but we'll get around that. We'll show you. If you see latch inferred anywhere, you know that you've hit a likely bug, right? Something you didn't want, right? The part that, now we might have latches other places, but if we see inferred, that is something we definitely don't want to see. So let's do a quick demo, all right? So what we're going to do is we're going to go to the lecture examples, week 1, day 3, and we're going to look at examples 2 and 3. And we're going to literally do what I just said, which is going to make stat, which is essentially the Yosys stat portion, and we're going to look to see if we can find latch infer. And we're going to do a slight modification just so that we can see it more clearly, since latch, like I said, is in the name of our file. So let's do that. So, all right, let's clear this up so that you can see pretty nicely what's going on. All right, so let's go to day 3 and example 2. All right, so if we take a look at this file real quick that's in here, what we're going to see in this latch demo is we're going to see 2 bugs. We have essentially an always with a wildcard sensitivity list, an if and no else. The second bug is the other one that we were mentioning, a case statement with 2 out of 4 potential branches listed. So that's what we have. let's do quickly here a uh, make stat, and let's do that grep that I was talking about. Let me run make stat once so you can see that it's just running the typical statistic thing, and we are getting all of our outputs. This is a lot to try to find what you're looking for. So the idea here is that if we grep, we can grep for specific keywords. And so we said that you could try to grep for latch. Now, when I do this, a lot of things show up. So let's try latch inferred. I'm just going to do it. Well, let's not assume that I know what tense it'll be. So latch infer. And so what we find here is we actually find two of them showing up here. The first one, latch inferred for signal. Which one? It looks like latch demo obug2 from process latch demo. Okay. And then another one here from signal latch demo obug1 from latch demo. Let's take a look real quick back at that code and see if we could find obug2 and obug1. Well, they're right here. obug1 is this assignment. obug1 would have to have a latch on it, all right, to hold this value of IA when select goes down to 0, right? This else branch that we don't have, right? Since we don't have logic that handles the other path, the inference is that we want to keep this value as is. And so right here, this is where the inferred latch gets attached to. Bug 2, same general idea. It is being assigned or latched onto obug2 because obug2, once it's assigned IA or IB on these two cases, if ever the opcode here becomes 10 or 11, well, we need to store whatever value we had before. And what we're storing is obug2's value. So that is what gets latched. All right, so how might we find these? That we've actually created some of these. I'm actually going to do a quick other grep, then I'll talk about it here in a second. Behind the scenes, this is getting stored in a very interesting way on our FPGA. And we'll talk about these, but this is going to be the key here. It found 8 SCCs. And so let's actually talk about that now. Should show you the fix actually before we dive into this. So let's look at the other module. Let's look at the fix of this. So that's in S3 example 3. Let's take a look. We're going to write the exact same commands. Let's do a let's do a make stat grep on latch infer and see if we see it. And what we see is no latch inferred. So there's no latch inferred for this signal, no latch inferred for this other signal, which is great. It's what we expect to see, no latches. Notice that it's not showing up as a warning, non-warning in iVerilog. Again, this is just going to be synthesizer dependent. We can also do this search. Again, I know I haven't talked about it quite yet, but SCCs, it didn't find any of these. And so we will talk about that here momentarily. If we take a look at the solution, the code that we ended up implementing here, um, you'll see that the difference here is this fix involves the addition of an essentially upfront declaration of ofix1 in all cases. And then the fix number 2 involves one, completing out the case statements and including a default value here. And this is just extra safe. So, um, all right. So with that, let's return back to what we just saw. So we just went through this. What's interesting is when we did the make stat on these, and again, I can show you one more time, make stat here. When we do this, you will see that there's nothing down here that says latch of any kind here, right? Didn't say latch at all. You'll notice 8 LUTs are used in the fixed version. If we go and we take a look at the broken version, and we do make stat, you'll notice we have 12 LUTs. So somehow more LUTs being used. in the broken version. So an indication that there is a difference between these. Let's see why that is. Basically, there's this, and I did a grep for it, there's these combinational feedback loops that are being created when we are, um, instead of these latches, well, it's a latch that is forming essentially a very strong feedback loop. And so let's take a look. Because this is a really hard bug to find when we are in the FPGA world. So question is, what did the tool actually build? So it inferred latches in the buggy version, but there weren't any D flip-flops or no latches, nothing like that that showed up. It basically showed us 12 LUTs wired into 8 combinational feedback loops. That's one per output bit, because each one of those were 4 bits wide. Um, in the fixed version, we ended up with 8 LUTs, no feedback loops, right? So on an FPGA, especially our lattice ICE40, there's no latch primitive. There's not a latch thing. And so Yosys will actually take the latch and it has behind the scenes a mapping that will convert it into a mux plus inverter. And basically that's what ends up happening is you get this mux and inverter that form a latch. And so what we see on the output are just LUTs. And so that's super hard. When you just look at it, you don't see like that there's a flip-flop that was generated. So again, a really hard thing to find if you have an inferred latch, especially on an FPGA. So how to catch it? You do a grep or a search in the Yosys log for latch inferred and check the SCC count. So the SCC count is essentially a combinational block that has a loop in it. It is a very strict feedback loop. Latch-free combinational module should have 0 SCCs, and in general, every inferred latch bit adds at least 1 feedback loop. So that's how you can tell. So where do these latches actually exist? So if we're talking about, we have Verilog here, you could go to 2 different targets. We haven't talked too much about the ASIC side, but there are primitives called latches in ASIC designs. And so you would get synthesis that would map an inferred latch to at least one of these characterized standard cells. And so you'd be able to see them in the netlist. On the FPGA side, again, depending on which actual FPGA you're using, what you're going to get is a LUT plus a feedback loop. So there's not a latch primitive in our current fabric. So Yosys will take that latch and map it into essentially the structure that you see here. Basically Q equals, if it's enabled high, you're going to get D, otherwise you're going to get the value of Q, and it basically will continue to cycle like that. So it's a very simple way to get a latch. So this matters because on the ASIC side, the bug is at least visible in your cell list. But for us, on our ICE40, it disappears into the LUT statistics. So really hard to find this. The only fingerprints are if you find latch inferred in the warnings and a non-zero SCC count. So those are the things to look out for on your FPGA synthesis outputs. Okay, so you should check the machine. Take this code, right? Take one of these always blocks that only has a branch and ask an AI system, will this infer a latch on, again, the device you have? So for us, the ICE40. If so, give me 3 different fixes. Ask the AI what fixes, predict what will it come up with. Will it come up with a default? Will it come up with an explicit else? Will it rewrite it entirely somehow? So good AI system should identify latches and suggest all 3. Weak AI might miss a default at top pattern. At the end, latch hunting is a well-solved problem. AI should work reliably here. Use it as a second pair of eyes. Okay, big takeaways. Latches appear when any input combination leaves an output unassigned. Right? So this is not always trivial, but basically you're missing some input combination where some output doesn't get assigned. 3 general fixes: putting a default on top, completing your if else, and then case statements with a default catch-all. Default on top is universal. I recommend you use it always. grep for synthesis logs for Latch or inferred every session. I would have a zero tolerance policy on this. You should do it. I should mention, the style of putting default on top being universal. I say that, and then, every company is going to have their own style or preference. So take universal to mean it universally works. But again, you're going to end up matching the style of the space you're in ultimately. So just keep that in mind. All right, every output, every path, every time. So no matter what form it takes, however you've got to do it, any of the three fixes I've provided, if you don't assign it, the tool will store the value. Okay, so it it does not make assumptions on what you wanted, right, or what you meant to have happen. It will infer a latch if you have a value that is not being assigned in every possible case. So we're going to move on in our next section on blocking versus non-blocking statements. Most of the time, actually, so far, we've seen the use of blocking statements in every single one of our always blocks. In our next video, we're actually going to introduce non-blocking for sequential logic. And so we'll preview the use of essentially the equal sign for combinational statements and our non-blocking for sequential. You should never mix the two. And our next topic is going to show you why. But we'll need the rule in memory before you get there. So we're going to show you that in this next video, still part of this sequence. But we'll use it extensively as we move to other topics. Thanks again, and until next time, keep building cool stuff.